Can you all hear me okay?
Yes.
All right. So let's start. So we have quite a bit going on right here. So your next exam is on Thursday, chapters 26 through 28. So you only have to do chapter 28 homework, although it's there's quite a few problems in it. The web assignment is due on the 24th. I hope you can get it done maybe a day before it. That way you can focus on the exam. Okay. The capacitor calculation worksheet is due tonight, and the other one's due Sunday night. These go pretty quick, I'm hoping, because I think one of them I did in the video, the last lecture before the second exam. And then one of them might be in your book. The last one is the harder one, but people have been asking me questions on it, so I'm hoping people got done with that. This should go pretty quick. There's some version of this problem in your book.
Hey, Professor.
Yeah.
I was talking with somebody else about how to do the capacitor calculation worksheet to see if we got the same things, and I noticed that two of us, the person and I, have completely different worksheets. Mine asks me to integrate the electric potential at some point between the two shells, and theirs asks to do it from one shell to the other shell for the bounds of integration.
I only put one sheet on Canvas.
Yeah, well, I thought so too, but mine says, my capacitance calculation worksheet says, integrate the electric field and the electric potential to some point R between like the shells of radius 1 and radius 2,
Yeah.
And theirs says it like gives an example of the integral, and the bounds go from R1 to R2.
Which problem is this one again?
I think all three of ours are different.
Which problem on the worksheet though?
All three of the problems on the worksheet are different.
Wait, the one that's due tonight, that's the one with the two spherical shells for the first question, right?
Yes, and then the cylindrical, and then the two spheres far apart.
Yeah, and you're saying they're...
Yeah, because it's asking us the exact same problems. Like, that person's is also asking them to find the electric field, then the potential difference, and then the capacitance. It's not the capacitor with the thin plate and then the thick plate. It's the same questions, but theirs has different bounds of integration and even shows them the integral in the problem.
Oh, so did I upload? Let me take a look at what's on Canvas.
I literally just clicked the file that's on the assignment on Canvas.
Can you share your screen?
I'm on my laptop right now. Let me get my iPad to join this, and then I can. It'll take a second.
Okay, but I can do it right. I can do it now. I thought maybe you had it. I'll do it myself. That's fine.
Okay.
Let me find the file. Okay, so just to be clear, this is the capacitance worksheet.
Right.
Okay.
And that's the second one, right? The one that's due later?
Yeah.
Oh,
So
okay.
Let's see if I can get the other one here. I actually have to go look at the sent email, I think. I don't know if I put it on there.
Oh, did you send us an email? Because if that's the case, I got the one straight from the assignment. I didn't get one from my email.
I thought I emailed it to you folks.
I got it under the modules on Canvas.
Yeah, me too.
Okay, let me look at the modules. I forget already because I'm emailing so many things, so I forget. Let me go to modules. Okay, so this is the version. I mean, is that the version you have?
No, that is not the version I have. Oh, you know what it is? I just realized I didn't download the right version of it for transferring it to my iPad, so it's just missing the equations. Like it doesn't have the correct formatting.
Oh, okay.
So, but I have a quick question because my problem is this. So, look at 1b really quick. It says use the equation delta V equals blank to derive the expression for the potential difference between the two spheres. When you said between, I thought you meant at some point between, not like from the inner surface to the outer surface.
Well, but that's still between the two spheres, right?
Isn't it not? Because if that's how you do that, then I got a part of problem.
Right, when you go, you're going from you're finding the potential difference between one sphere and another one.
Right, and that makes sense if I'm trying to, trying to lead up to the definition of capacitance. But if I'm trying to find the electric potential at some point between the two spherical shells, then aren't I going to integrate from R2 to some point R between the shells?
Correct, but we're not doing that.
Okay, I guess I just, when you use the word between, I assume that's what you meant, but that's my fault. Okay, thank you.
Okay. All right.
If you were to do that and find the potential at some point, you would need the charge of the point, right?
No.
To find it in between,
Yeah.
you would just integrate to some arbitrary point in between. You would call, instead of calling it R2, you call it R, whatever it is.
Oh, okay.
Okay. Okay. So let's continue.
Professor?
Sorry?
Can you hear me, Professor?
Yeah, I can hear you.
Can you hear me?
Yeah.
On number 2 on that worksheet, I keep getting an extra L.
You keep getting an extra L?
Like, I think there should be an L there maybe, even though I know we aren't given one.
Well, and that's a mistake on my part. It's the capacitance per unit length you have to calculate. Oh, there's a mistake in there. It should look, the equation should look like this. And of course, if you look at the video of the last lecture I gave before exam 2, should look like that. Okay? So yeah, that was a typo on my part. I don't know why. I thought I put lambda in there. I guess I didn't. Okay. But yeah, if you want to double check, look at the video, the last lecture of the previous unit. I don't understand. I'm sorry. You're calculating this. Okay. The capacitance per unit length. Again, go back to the video, because I completely solved the problem in that video.
Hey, Professor, just to clarify, the natural logarithm is actually in the denominator of the
Yeah, you're right. Sorry, I'm sorry. I'm just in a hurry because I'm trying to get it. I'm trying to get starting the lecture.
Yeah.
So
right,
okay, if you have more questions, please ask them at the end of class, because I kind of need to get started on this, and just hold off on them, and then I will take time for at the end of the lecture. You can ask me your questions. I'm sorry, I'm just trying to go fast because I want to begin the lecture and discuss these examples. Okay. All right, so yeah, like I said, you have more questions, and some of you guys might have lab questions. Ask them at the end because I've seen some in the chat. So I'll use some time at the end of class for that. And by the way, next Tuesday I'll take the time out at the end of class to answer your questions on the homework. Okay? All right. So what I want to do is another example really of the circuit I did this morning. But it's not balanced. So I want to do this particular case, and I set it up so it's not balanced. And the question is, what is the current that's going to go through the ammeter? Okay? When you do the DC circuit lab, oops, I think I forgot to start my other video. And I got to pin myself. Sorry. Oh no, I did start the video. Okay. Let me go back here. When we do the DC circuit lab, this is what you're going to be, one of the circuits you're going to be doing. Okay, so pay attention to this because on Thursday, the following Thursday, this is the lab I'm going to talk about. And what you're going to do is you're going to be making measurements of this system. Okay? So I'm going to assume an ideal ammeter. All right, I'm going to assume an ideal ammeter. So that means its resistance is what?
0.
0, okay. So R equals 0. So that means then I take these 2 points in time together. What does that say about these 2 points then? I'll call them 1 and 2. It's the same thing as I use same thing as if I used a wire. It's no different than me doing this. What does that mean though then?
The equivalent resistors are in series right there.
Well, let's be careful. I'm just talking about point 1 and point 2.
No
Right.
current is flowing through there.
Well, the only way no current is flowing through it is if we satisfy the Wheatstone bridge equation. And I purposely chose the resistor so it doesn't satisfy the Wheatstone bridge equation. So current will go through it. But if I tie these two together, let's see, delta V is I times R. If R is 0, what does that mean?
There's not going to be a change in voltage.
Correct. So this point and this point are at the same voltage. So that means that V1 equals V2 because the ammeter has no resistance. Okay? So let me just say this means that I can't spell. V1 equals V2. Okay? Well, so if V1 equals V2, how are these two resistors connected then?
Parallel?
Yeah, these two are in parallel and these two are in parallel with each other. I'll redraw the circuit in a minute. Let's consider the current going through here. Okay? So the battery, the power supply, it's not a battery, it's 300 volts, is supplying current this way. It hits this node. It's like hitting a T in a pipe full of water, and then the water will take two different paths. Some of the water will go this way, and some of the water will go this way. So it splits into two currents. This is I1, and this is I2. So what should I call this? If this is I1, this is I2, what should I call this?
I1 plus I2.
Good. That's Kirchhoff's current rule, by the way, or Kirchhoff's current law. All right, that's KCL, that the sum of the currents going into a junction equals the sum leaving. Or the other way to write it is the sum of the currents equals 0. Just it depends on how you write your I's. Okay? So if there's a current here, if there's a current going through the ammeter, what will happen is you're going to get the current to split. You'll get a current this way, and then you'll have some current this way. Now, the direction of this arrow is going to depend. Well, what's it going to depend on? How do I know the current's going to go to the right or to the left? This goes to your question you were asking, Rob Tesh, in lab. How do I know the current's going to go to the right or left?
The least resistive path that it gets. Like it is based on the resistances on top.
Yeah, I'm going to have more current here than here. Isn't that true?
Yes.
So this current's got to go this way. In fact, these two are in parallel, and they're going to have the same current going through them. The current's got to go this way. Because there's going to be more current here because the resistance here is lower than here. All right, this voltage and this voltage are the same. So we can already use our intuition to say that the current's going to go in that direction. Okay? And so some of it will go this way, and then the rest will come down this way. And so what will happen here is this plus this will give me this current, whatever that is. And I'm not going to, let me not assign currents yet because I don't want to confuse things. Okay, are we okay with that? Mm-hmm. And when you do your lab, when you do this lab, this is what you're going to do in the lab. Okay, you're going to measure the current here, and you're going to measure the current here. It's going to be kind of a tough lab because you actually need three meters, but we don't have 3 meters. So this will always be there. Okay, but what you're going to be doing is you're going to measure the total current here. You'll measure the voltage here and the voltage here. Voltage divided by resistance will give you current. Voltage divided by the resistance will give you current. And what you're going to see is if you're obeying Kirchhoff's laws. Okay, so that's what we'll talk about it more next week, but this is the lab. This is part 2 of the lab. Okay, part 1 of the lab, you're not gonna have this ammeter there. All right. Okay, so let's go on. So we know that these so R3 and R6 in parallel. R2, oops, let me write it this way. Bottom 2 resistors in parallel. Which means I can redraw the circuit. Let me redraw the circuit. So I want to make sure I'm not drawing too far down on the board. 3 kilo ohms, 6 kilo ohms, 2 kilo ohms. It's very hard to write like this, especially when you're left-handed. And remember, this wire is no different than if I just join these two together, okay? I just put the wire there. So these two are in parallel. Can I replace those two with a single resistor? The answer is yes. So in the end, I can get this. What do I get when I combine these two?
One-half of an ohm.
Okay, you did it quickly. Good. So you get this when you add these up, you get a half, and then you take the reciprocal as what?
2.
2. So this is 2 kilo ohms. Good. And when you combine these two, what do you get?
1.
1. Okay. So my equivalent resistance of the circuit is what? 2 plus 1 is?
3.
3. Okay. Well, 3 kilo ohms. Okay. So let me use a different color. What's the current through this thing? And tell me if you can't see the colors, because I'm going to use like, well, I guess I can use purple. Let me use purple.
Is it 100 amps?
Not 100 amps, but 100 milliamps.
Right, yeah.
So there's 100 milliamps through this one, and 100 milliamps through this one. 0.1 amp, okay? So what's 0.1 times 2,000? I want the voltage.
200.
200 volts. Can you see that?
Barely.
Okay, let me use blue maybe. Actually, let me get another color. Let me get a brand new one.
For these calculations, you're just using Ohm's law, correct?
Yeah, I'm just using Ohm's law. I'm just using Ohm's law, and really that's it. So I chose nice numbers so I can do the calculations quickly. What's this voltage going to be? What's 0.1 times 1,000?
100.
100. Is there another way to figure that out? Well, if this is 300 volts, and that's 200 volts, what's left?
100.
100. So this replaces these two, so both of these have 200 volts across them. And these two have 100 volts across them. So I can do the bottom one. This 1 kilo ohm resistor replaces these two. So the current is split equally between these two. So what's half of 100?
50.
50, okay. Okay, so I have 50 milliamps on each side. So if you're not sure, you just take 100 divided by 2,000, you get 0.05. Okay, if you want to do it that way. Let's do the top one then. What's 200 divided by 3,000? It's 0.066666, etc. So let's just write 67 milliamps. What's 200 divided by 6,000? Or what's 2 over 6? It's 1/3. So this is going to be 33 milliamps. Okay, so I have 67 milliamps here, 50 milliamps here. How much goes that way? What's left over?
17 milliamps.
Yeah, 17. So 17 milliamps goes through the ammeter. Does it check? Well, let's see. This side was 33. This is 50. So you have 17 going this way, 33 going that way. What's 17 plus 33?
50.
Okay, so it works out, right? And so when you do the lab, you're physically going to measure all this. Okay? You're physically going to measure this when you do the lab. This circuit kind of really shows you how series parallel works and Kirchhoff's laws work, which I'm going to talk about in a few minutes. Questions on this?
I have a question.
Okay.
If the two resistors which are on the bottom, if the one on the left was 1 and the one on the right was 4, would you still get a choice for the direction?
If this one was 1?
Yeah, the one on the left was 1 and the other one was 4.
Of course, that's going to change everything, right?
Yeah, like the current can go through one entire path, so it can either be from 3 to the ammeter, then to the 4 kilo ohms, or it can be 6, then ammeter, and then 1 kilo ohm.
I might not be able to figure out the direction intuitively.
Mm-hmm.
Okay, but that's okay though, right?
So if like the resistances add up to the same value, since they are in one like single line, would that mean it's like the resistances add up to the same amount in both cases?
If this is 1 and this is 4?
Yeah.
How do you know that? You have a 1 here and a 4 here, they're in parallel. That's less than this.
No, like if the current goes through the 3 kilo ohms and then through the ammeter and then through the 4 kilo ohms.
I'm not sure you mean this way?
The current goes through the whole entire circuit no matter what the resistances are. It's all about the proportionality depending on the resistance. There's just like a proportion, like if it's a higher resistance, there's just less proportion going through that resistor. There's still proportion through the resistor. Like proportion of the current.
I mean, if this is 1 and this is 4, what might happen is you might end up getting the current this way. I'm sorry, you might get less current going this way, going through here. You might get more current going in this direction. It just depends, and of course, intuitively, I probably couldn't do it off the top of my head.
Okay. Mm-hmm.
It's right here, Chase. I'm not sure. It goes this way. Some of it goes this way, and then look at the arrows. This is this plus that. Is that okay? Yeah, you just gotta follow the arrow. So if I chose different numbers, it's possible I won't know the value off the top of my head. Like in the numbers you gave me. It would be a little bit harder to see. But, I mean, I can still solve the problem. Are you just trying to get an intuitive... Are you trying to just use your intuition to figure out the direction of the current?
Yeah.
Oh, okay. Because you don't need to. I mean, that's the thing. What's nice is you don't need to. Wait till we do the Kirchhoff's law problem.
Okay.
Because you'll actually have no intuition as to which direction it goes, and that's okay.
Yeah, it's just that usually with problems, I try to see the thing moving and then find an answer. And I just don't prefer doing everything mathematically because, okay, that is there, but I also would want to see things happening physical, like conceptually.
Oh, I understand. I mean, and it's really good that what you're thinking about. It's just that there are some cases where you can't. I mean,
Yeah.
in fact, you experience the torque problems in Physics 205, and that's you'll see problems where you just have to guess the direction for a force, and if you're right, then you get a positive answer for the force. If you're wrong, you'll get a negative answer, but that's okay because you don't have enough unknowns, and that's going to happen. It just depends on how many knowns you have. I mean, I have to think about it in your case a little bit, and then I could probably figure it out.
You might be able to go use the tool that was in the like the lab discussion that he gave us. That was like a circuit building tool. You might be able to use that and just play with it
To develop the intuition?
It just came to my mind right away, so I can use that later. But
Yeah, I mean, intuitively, sometimes maybe I just don't see it right away, but you might be able to figure out which way the current will go through here. I don't always see it right away. I just solve it, and then I just look for consistency. In other words, is this current going to be consistent everywhere in a circuit, like it was here, right? This is this guy plus this guy, and then this is this guy plus this guy, and this one is this plus that. As long as it's consistent, you're fine.
Yeah.
Okay. All right. I'm going to come back to the next example later because I want to get to Kirchhoff's laws. Because the last example might take me a little while. I kind of want to get Kirchhoff's laws, and I'll do that. I'll do the next example in your notes. But I think it's important for us to actually eventually get to Kirchhoff's laws. There are a couple of questions I want to ask you before I get to Kirchhoff's laws. Okay. So let me skip this example. I'll get to it. Okay, it's a fun one. By the way, you can draw that in this simulation and solve it. So I want to say something about internal resistance real quick. Because sometimes this drives students a little crazy. And I remember learning this when I was a student, and I actually had a hard time, even though it's not a hard thing. Okay. What is the effect of internal resistance of a power supply? Power supplies are designed so that their internal resistance is low. Okay. Right? They're designed so that the internal resistance is low. So let me draw this circuit. This is more of a realistic power supply. And this is, we'll call it the load resistor. It could be, whatever device that has a resistance. It could be a light bulb, it can be a refrigerator, whatever. Okay, and this is the internal resistance, and then we draw a little box to make this power supply realistic. And I don't know, there's a video, and again, I go back to that guy Electroboom. He actually talks about two different types of schematic diagrams. Those that are very accurate, that take into account all the little details that can affect your circuit, and then there's a really general one where you ignore this stuff. Okay. Generally, power supplies are designed so that this is really low. So what happens when you have an internal resistance and you hook it up to some bulb, some kind of load like a light bulb? Well, if this thing is 3 volts, this ain't going to get 3 volts. Right? The equivalent, the total current is going to be your 3 volts over your load resistor plus your internal resistance. I'll use the letter script E for the EMF. Okay, and so the voltage across this is going to be this current times that resistance. So all I'm doing really is I'm solving a problem where I have two resistors in series. This is just a series circuit. This is actually called a voltage divider because each resistor takes a certain fraction of the total power supply voltage. And so your power dissipated is going to be, the power dissipated by the load is going to be the product of these two. Let me know if you can't see the board. So how do you see this effect when this gets bigger or when the current's big? Do this if you get a chance, if you have on your car, okay? Have someone in the car turn the headlights onto the car and you're standing outside. Then turn the keys to start the car up. When you're turning the keys, there is a lot of current going through your car as you're turning the keys. This voltage drop is going to be large. Your headlights are going to get, the voltage across the headlight will get smaller. And what will happen to the headlights as you turn the key?
They're going to be dimmer.
They get dimmer. Okay, so you'll see the effect of the internal resistance of your battery. The older the battery, the bigger this is, the more the effect. Okay. Now, obviously, your car circuit is a little bit more complicated than this. Okay, I'm just simplifying it, but the idea is still the same. Is that you turn the key, you're drawing a lot of current. This is going to have a significant voltage drop.
Wait, so that P is the total power or the power lost from the resistance?
This is the power lost by the resistor, by your load. So when is that
okay.
maximized? How do you maximize that? How would I figure out when it's maximized?
Take the derivative.
Yeah, take the derivative. Okay, so let's do a little calculus. One of the few times we do calculus in this unit. So I'm going to take dP over dr. I want to find for what value of the load resistance is this maximized. Okay, I never remember the quotient rule, okay?
Just use a negative and do a...
Yeah, I do this.
Do the product rule.
Yeah, I use the product rule. I don't know, I just remember it that way. And so what do I get when I do this? Let's see. Does that look okay? And then I set this equal to 0, right? I find the critical point. Okay, I'm not going to do the second derivative test, okay? Okay, I don't have to be as rigorous in this class. So basically, I just need the stuff in parentheses to be 0. If I get a common denominator, what do I get?
Negative r minus r over r plus r squared. Or cubed, sorry.
Did I make a mistake? Hold on a second. Oh, I screwed up. That's not right. Right? Okay. I was looking, I was like, there's no way I'm going to get the right answer from that. I know the right answer ahead of time. So I set this equal to 0. And so what do I get here? I get little r minus big R over... Basically, I just need the numerator to be 0. And that's when I get maximum power transfer to the load. And in the past, we've actually done this, had you guys do this lab, where we would fake an internal resistance. Because the power supply internal resistance is really tiny. Okay.
Professor?
Yeah.
Is the voltage drop the highest only when we start the car and not afterwards?
It's only the voltage drop across the internal resistance, you mean?
Yes.
Yeah, because that's when it's drawing the most current, because that's where you're drawing a lot of current through the circuit.
And then it decreases?
Yes.
Okay.
Once it started. So how are devices connected into your house? Series or parallel?
Parallel.
Yeah, what would it mean if it was series?
You wouldn't be able to choose what things were on and what things were off.
Yeah, just imagine this. We'll use our imagination. So here's your AC power from your house. And then you go to a light bulb. And then your air conditioner. And maybe the refrigerator. And the power goes out. Or no, not the power goes out. The light bulb goes out. Then what?
Nothing else works.
That's right. Okay, let's think of something else. Another thing. If this is the case and it's working, which one's going to have the biggest voltage drop?
The light bulb?
Yeah, this is what, 25 watts? This is about 6,000 watts. And this is probably about 1,500 watts. Ballpark figures. Okay? These are rated at their voltage. Actually, an air conditioner runs at 240, but imagine if that's a W. That's okay. You saw the demo with the light bulbs. Which one was lit the most?
The lowest power one.
Yeah, because it has the biggest resistance. So you do not want this in your house. So everything in your house is in parallel. Okay? Everything in your house is in parallel. The two outlets, on your, whatever, every outlet, you basically have two outlets. They come in pairs. They're connected in parallel.
Is that how they can guarantee that each outlet has the same voltage?
Well, it guarantees that each device that you connect it to has the same voltage, right?
Right, yeah, I guess.
Yeah.
That's...
How is the circuit breaker connected?
In series?
Yeah, because... So here's a circuit breaker. What you want is everything to go off if something goes bad, right? So you put this in series with everything else. So each set of parallel, because each in your house, if you go to a fuse box, everything's connected in parallel, and so you'll have a circuit breaker for each leg of your circuit, right? So you'll have something like this. I don't want to do the air conditioner because the air conditioner is 240. Here's your power supply. So here's maybe some bulbs. This is one room. And we'll put the circuit breaker here. And then here's your fridge. And so we'll put another circuit breaker here. So this is in series with the fridge. And then you have another one for something else, whatever the heck it is. This could be your living room. Okay. 1 or 2 outlets in your living room, for example. And so if these go out, then, right, if these go out, then just this section goes out. But if the main one goes out, because you also have a main one, then everything goes out. Okay. What's the purpose of the grounding prong? It's to protect you in case of a short. In the old days, we didn't have a grounding prong, so that if you were using a dishwasher, you don't want to get electrocuted. You use not a dishwasher, but a washing machine, and then there was a short. You touch the washing machine, you're dead. Okay, so that's what the purpose of the grounding prong. So the chassis, the body of the washing machine is grounded. And then what happens to the internal resistance of the battery as it ages? It increases. So I'm asking you these practical questions because you should learn these things, right? And in fact, at some point, especially if you're an electrical engineer, you should be able to like put a switch in your house, or like add a fan to your house. Or for example, I have a friend who's an electrical engineer. He installed his own solar power by himself. Saved a lot of money. Okay, so you're learning skills that you can use at home. But I'm not telling you to do stuff now because I'm not really showing you all the. We're not talking about all the safety hazards around your house either. But eventually, you're going to learn how to do things around the house. Okay. Let me do one more example, and then we'll get to Kirchhoff's laws. And this is really an example of Kirchhoff's laws. Suppose I have that circuit. I'll draw it up here. And I'll draw it this way. Okay, it's not a great drawing. This is 2.5 kilo ohms. This is 5 kilo ohms. This is 9 volts. And this is 1.5 volts. I want to know the current. I want to know what's my current. If I put an ammeter here, what's the ammeter going to say? What's the ammeter going to tell me? How do I do this problem?
You add the voltages to get the total voltage.
Yeah, I'm going to go around. What do I know? And we talked about this the other day. This is the loop rule. So we can say Kirchhoff's voltage law. People will call it KVL or KVR or whatever. The sum of the voltage drops around the loop is 0. The sum of the voltage drops is 0. Really, the sum of the delta V's, I should say, the sum of the delta V's is 0. So let's say that this is at 0 volts, this is at 9 volts. If current goes in this direction, I could be wrong, but I'm going to choose the current to go in that direction. Then what will happen is the voltage will go from 9 volts to something lower here, and then it'll go from 2.5 from whatever it is here to something lower, whatever it is here. Okay. And then the voltage will go up. And when I look at all the voltage drops, I'm going to get 0. So what that means is the sum of the V's equals 0. So if I go around in this direction, in the direction in which the current, the charge flows, then I say, okay, I'm going to have 9 volts. Oh, the voltage increases, so plus 9 volts. The voltage across this thing is going to drop, so I say minus I times 5.0 kilo ohms. Then the voltage will drop again. But then I go from a lower voltage to a higher voltage. So this 9 plus 1.5 is 10.5. And these are gonna give me minus so I is going to be 10.5 volts over 7,500 ohms, which gives me, if I look at my answer here, $13 milliamps. That's my current. Okay? This is a prelude to using Kirchhoff's laws. Because what I want to do is solve this circuit. I want to solve this circuit. I want to calculate the current through each one of those resistors.
Professor?
Yes.
Is the current on one side of the battery or the power supply always the same as the current on the other side?
You're talking about the example I was showing?
I mean, like for any example.
You mean the current on this side and this side?
Yeah.
Yeah, right. This is in series, right? There's no other place it can go, right?
Oh, okay.
Right. Just imagine a water pump, right? If this was a water pump, with water flowing through it, the water coming in, the amount of water coming in here, the amount of water going there is going to be the same.
If there's a capacitor in the circuit, would that still be true, or would it change before it gets filled up?
Are you asking will the current change, or are you asking will the current I don't want to say will the current in my circuit be the same before and after the capacitor?
I mean, like, will the current on one side of the power supply be the same as the other one?
Yeah, because again, there's no other path. There's no other path to take.
Oh, okay.
Right.
I just wanted to clear that up.
Yeah.
Thanks.
Yeah. As long as the only way the current's going to change is if you have a T. Okay, it's not a good T, but so water can go either this way or this way. Just think of it in terms of water. So that's the only way. So there isn't a second path, right? If I put a capacitor here, I have not given the electrons a different path, right?
Yeah.
And so they still have the same path. And so the current's still going to be the same. I mean, it's a good question to ask. Okay. So now let's tackle this problem. This is really this problem has really everything that we've covered on circuits except capacitance. We can throw that in when we do RC circuits on Tuesday. So what I'm about to do, you can apply to every circuit you solve in this course. Every single one. It's just that it's much longer. Okay, so when you take Engineering 17, you will learn tricks to make the problems easier. we don't have the time to go through those tricks. Okay. So let me draw my circuit. So I have 5 resistors. Actually, you know what? I'm going to draw it. No, I'll draw it here. That's okay. All right. I want to find the current through all of those. Okay. So what ideas do I? Oh, I didn't even show I didn't even show the picture today. Oh no, we're okay. To solve this, we have to use Kirchhoff's laws. The loop rule, the sum, so we got to use the sum of the voltage drops in a loop equals 0. There are a lot of loops in that picture. How many are there? There's like 4, right? Well, there's at least 4 loops. Maybe there's just 4 loops. I didn't spend time counting them. Okay? You don't need all 4 loops. So we're going to use the sum of the voltage drops equals 0 like in the previous problem. But also you're going to use the junction rule or KCL, Kirchhoff's current rule, that the sum of the currents going into a junction or node equals the currents leaving a junction. So what is our methodology? And this is one of the things students have trouble with. They don't have trouble with, they don't want to do, is they don't want to draw a picture. And you don't draw a picture here, you're in trouble. You first got to draw a nice large version of the picture. You got to draw the picture. You got to draw a large version of the picture. And I would apply the current rule right away, because that's going to tell me how many loops I need to solve for. And I'll show you what I mean by that as I go through the example. So there is a methodology. I'm hoping that you follow this methodology, and you actually don't have to follow this methodology. You will find that there's a lot of different ways to solve this problem. If you go online and you watch Electroboom talk about Kirchhoff's laws, he does it a little bit differently. Okay, I'm not even following our textbook. I'm following a different textbook. And I'll tell you the textbook in a minute. So you choose loops and then sum in the direction of delta V's. Okay, so you go around the loop adding up the delta V's as you cross them. And you choose as many loops as you need so that you cover all your unknowns. And then solve equations simultaneously. So there are cases where you can do, you have 6 loops and you have 6 equations and 6 unknowns. And that'll happen in Engineering 17. But your professor what he'll have you do is use your calculator to solve them. Because your calculator can do 6 equations and 2 unknowns, no problem. Okay, and you'll see in our homework, we're probably not going to go more than 3 equations and 3 unknowns. I just want you to know how to use the idea. When you take Engineering 17, you'll do 6 equations, 6 unknowns, or 10 equations and 10 unknowns. All you got to do is put the equation into a calculator and it does everything for you. Okay, the goal here is to learn how to set them up. So your notes, I skipped, you'll notice that some of the notes are hidden in your PowerPoint. You can read through those. I want to do this example. So before I do the main one, I want to do a simple one. So you get to see how this works. But our goal is to do that one. I want to do a simpler one first. Okay? So you get an idea of how this works. So the first thing I got to do is draw a picture. So there's a circuit. This represents, for example, how the alternator keeps the car battery charged. Okay. So let me draw the circuit. So at the top I have 1.2 ohms. In the middle section, I have 0.01 ohms. And then I have the battery. And the battery is 12 volts. And this one is 0.01 ohms. And then at the bottom, .1 ohms. And let me make sure you guys can see everything. And the alternator is 14 volts. So let me connect these. And so this is A, B, C, F, E, D. So what do you notice? What can you say about the following? What can you say about those values?
All are equal.
Yeah, they're all equal to each other. Right, they're in parallel to each other, right? Mm-hmm. So what am I going to do first? I drew the big picture, and so the next thing I'm going to do is assign currents. And it doesn't matter how you do this. And this is the students have a hard time believing me when I say this. Okay? I'm going to say current's going to come from here, and it's going to split. Some of it's going to go this way, and some of it's going to go this way. Okay? And I'm going to be consistent with my notes. I'm going to call this I1, and I'm going to call this I2. So what do you think I'm going to call this current?
Of those two?
Yeah, I1 plus I2. So I have two currents that I don't know. I don't know I1 and I don't know I2. Okay. If I want to flip this around, I could. I don't know the direction of the currents off the top of my head. Okay. Now this goes to your question, Ravtej. I don't know what the directions of the I's are, really. I'm assuming the values. And if I'm wrong, I'm just going to get a minus sign in my answer.
I don't know either.
Right, and we don't know, right? But the thing is I know that doesn't feel comfortable. Okay, but I don't have enough information really to figure out which direction it's going to be. But as long as I follow the laws of physics, I'm going to be okay. And then I can use my intuition afterwards to see, okay, does everything make sense? I should get the delta V's across each one to be the same. So that is going to tell me that, if I'm right or not. So I do have ways to check, even though I don't have any intuition ahead of time. Does that make sense?
Yes.
Okay. So now I've denoted all my currents. The next thing, I'm going to sum voltage drops. And so because I have two currents that I don't know, or these two are independent of each other, and this is the sum of these two. I only need 2 loops to solve this problem. I'm going to sum voltage drops around 2 loops. And then I'm just going to solve them, and I'm done. So all the physics is in drawing this picture with those currents that you see there, and in me choosing the loops. So I'm going to choose the loops that you see there. The green represents the loops I'm going to choose. I actually have 3 choices. The third one is redundant. Okay, the third one will be redundant.
Wait, Professor, how did you know that the voltages across CD, VE, and AF were all equal?
Aren't they all in parallel?
Yeah, but there's 2 power supplies, so doesn't that like change it at all?
But they're in parallel. Right? Aren't they in parallel? We already established the fact that when things are connected in parallel, their voltages are the same. Isn't it true that this is just a wire?
Yeah.
And so it's the same thing as if I squish this down to nothing. This point and this point are connected at the same place. I can make this wire smaller and smaller and smaller so A and B touch each other. All right, I can draw it like this.
I mean, like if you combine the resistors and the
No.
and the batteries.
I'm just shrinking the wire. It's the same thing.
I can't see where you're writing.
Oh, sorry.
Yeah.
Thank you. It's the same thing as if I did this. Right?
Yeah, but what happened to the CD part though?
Yeah, but what I'm saying here applies to what happens above, so it doesn't matter. Isn't it true that this bottom part is the same as that bottom part?
Yeah.
Okay, so that means that, I mean, this is A and B. In fact, this is A, B, and C. So I can do the same thing up on top. And this would be F, E, and B. So they're all in common. Now, in a sense, you're kind of right. I mean, these do have resistances, but we're ignoring them. We're ignoring the value of that resistance. Okay? Or I can say that this length and this length are the same. So it doesn't matter. That doesn't play a role. Okay? This and that are the same circuit. You don't look convinced. You don't sound convinced, Vincent.
Yeah, I don't know. It's just kind of hard to wrap my head around. Like, I don't know. I think it's because there's a battery on each of them, and that's what's
doesn't matter.
throwing me off.
I mean, you did the multimeter quiz, and you hooked up the batteries in parallel. If you measure the voltage across the bulb, it's still going to be 1.5 volts. Isn't that true?
Yeah.
Okay. So what you can do, there's that simulation from online. You can actually play around with that simulation and see for yourself. Better yet, you can actually wire something like this up with the batteries that you have. You don't have to have a 12-volt battery. You can put a 1.5-volt battery here, another 1.5-volt battery here with some resistors, and you can see for yourself that you get the same results.
Oh, okay.
Okay. I think what you're missing is that that when things are in parallel, the voltage drop has to be the same across them. You're making this terminal and this terminal the same value, the same voltage. Okay, so let's move on. So I'm gonna sum voltage drops this way. So I'm saying the current is going in this direction. I'm summing the voltage drops clockwise. The electric field and the current are in the same direction, right?
Yes.
So that means that, and the voltage decreases in the direction of the electric field, right?
Yes.
Okay, so having said that, let's sum voltage drops. Let's go around this, let's do the bottom one, let's go this way. Okay. I start here and I go across the battery. I go from a lower voltage to a higher voltage, that's a voltage gain. So my current is going this way. The current, the electric field is that way. The voltage drops in the direction of the electric field. That is a voltage drop. I get that. I didn't put the zero there doing this because I'm going to run out of space. Then I go around here. I'm summing in the direction of the current. Another voltage drop. And then what happens when I go across the battery? I go from higher voltage to lower voltage.
We can't see all the way over there.
Oh, sorry. Let's... Okay. Now, let's do the top loop.
Wait, isn't that plus 12 volts, or is it because you're going from the positive to the negative?
It's negative, right? Because you go from higher to lower, that means negative.
Oh, okay.
Okay. So let's do this loop. I'm going to go clockwise. Let me start here. I'm going to go that way. Now, when I go in this direction, I go from a lower to higher. And again, I'm dropping things to save space, okay? So now I'm summing against the electric field. The electric field points towards me. I'm going in the opposite direction. I'm moving in the direction of increasing potential. So that's a voltage gain. And then I hit this resistor. Again, the current's this way. So I'm summing in the direction of the current. So that's the voltage drop. Okay, so those are my equations. So let me rewrite these equations. 14 minus 12 is... Oh, I have minus 0.1 I1. What else can I do here? Minus 0.11 I2. Please check my math. If you see a mistake, just stop me. Because it's always easy to make a mistake. The physics is done, now it's algebra. So now the next thing I'm going to do is say, okay, I don't want to do substitution, okay? I don't want to do substitution. Let's do this. I want to eliminate I2. Can I multiply the bottom equation by 11? Are you okay with me multiplying the bottom equation by 11? Yes? Okay, good. What's 11 times 12?
132.
What's 11 times 1.2?
Is it 112.1? Oh, okay.
All right, did I do that right? All right, let me do it in the calculator.
Honestly,
Yes, you did.
Okay,
You did that
okay.
right.
And then this is 0.11, right? Let's add them. So I1 is what?
Wait, wouldn't it be 13.3 because you're adding two negatives?
Oh yeah, geez, thank you. Okay, so when you do the math, you get 10.1 amps. So how do I find I2?
Plug it back into the equation.
Yeah, I just plug it into one of the other equations. I'll let you do that. So I2 is 9.0 amps. And then I1 plus I2 is 19.1 amps. So the directions I guessed for the currents were correct. Okay? All right, I do want to do the other problem. Okay, just because I think it's important, and it's important in terms of getting you started on the assignment. So if this is recorded, so if you need to leave, that's fine. You okay with this one? Oh, how do you know if you've done a redundant loop? That's a good question. If I would have just chosen, if I wouldn't have applied the current rule, you would get 3 loops, because the third loop is basically this big one. And you would find that the third equation would be the sum of these two. Okay, you would find that. And sometimes, if you've had Math 33, you learn how to do those things pretty quickly. Okay, if you've had Math 33, you can actually figure out ways to see if the equations are independent of each other. Okay, so you want the equation to be independent of each other. But by applying the current rule right away, you see how many independent currents there are, and that'll tell you how many loops you need. And so I like doing it that way. I actually, and so this method is is in a textbook called University Physics. By Young and Friedman. I like their way of solving these problems the best. Okay, so I'm just copying how they do it. I want to do this one. Okay, I want to do this one. So I'm going along, but I want to do it because it's so important. Okay. All right. How many times have I done this circuit already? And you're going to do it in the lab. You're not going to do this one in the lab. This one's a pain to do in the lab. Because you need like 5 multimeters at least. Okay, so I have this drawn. I left it there on purpose. So I want to do this one. So I already have my picture drawn. I have a nice big picture. Don't make your picture really tiny. Make it nice and big so you can draw on it. Maybe I should have made it bigger than this. I don't know. So what I'm going to say, I'm going to look at, I'm going to say, okay, this is 13 volts. So let me write down the power supply voltage, which I forgot. And I'm going to say, okay, there's only one power supply here, but I need to use Kirchhoff's laws. Why? Because the resistors are neither series nor parallel. They're not connected in series or parallel. So I use Kirchhoff's laws. I'm going to start with the current law. I'm going to say, oh, this is delivering energy, it's delivering current. And it splits up here, this way and this way. I'm going to call this I1, and I'm going to call this I2. And so if this is I1 and this is I2, and the current comes from here, then I'm going to say this is I1 plus I2. I don't know if this is balanced or not, and I have no idea which way the current's going to go through here, but let's pretend it goes this way. If I'm wrong, I'm wrong. The math will tell me I'm wrong, okay? So let's say I write that down. So what's this current going to be? What's the current through here going to be? Well, it's going to be I1 minus I3. Because this is going to be this plus this guy. If I sum these two, I get I1. Then what about this current? What's this current going to be? Oh, this is just going to be I2 plus I3. How many independent currents do I have?
3.
5.
How many subscripts do I have?
3.
3.
3. So I have 3 independent currents. So how many loops do I need then?
3.
3. So that's it. So I need 3 loops. Okay, so one of the things I do is I'm never consistent with my notes, so I'm going to have to use my notes for this one because I'll actually change things, okay, as I sum currents. Because I'm going to do this in a particular way, and I'll show you why, okay? Can I use a different way of assigning currents? Yeah, as long as I'm consistent with the current rule, I'm okay. In fact, in your notes, this problem is done twice. All right, in your notes, this problem is done twice. And I'll go through the other one briefly. I'll set it up, and then you can look at the entire solution. It's in your notes. And no matter how you assign the currents, you got to get the same answer. Okay, so now I got to choose my 3 loops. I can choose whatever 3 loops I want. There's a lot of loops here. So let me show you in the figure what I did. There's I1, there's I2, there's I1 plus I2, there's I3, I2 plus I3, and I1 minus I3. I guess I should draw arrows in the picture I drew on the board. So let me show you the loops I'm going to choose. Okay? I'm going to choose, I don't know why that one came up as number 2. I have to fix that. So that's one loop. That's another loop. Whoops. I think I went too fast. There's the first one. Oh, there's the first one. Okay. So those are my 3 loops. So let me draw them on the board. I'm going to use green. So I'm going to choose this loop. And I'm going to go counterclockwise just for fun. Okay. And I'm going to choose this loop. So it's this one. And then the third loop, those are my 3 loops that I'm going to choose. Hopefully the green is not too faint. Okay, so you guys ready? Let's do this first loop. So let me write down the values of the resistances, okay? R sub A is 1 ohm.
Wait, where does loop 1 start?
Well, just this way. It doesn't matter where you start.
I thought you had to start at the battery and end at the battery.
No, you don't have to. You do have to include the battery in one of them, right?
Oh, okay.
Right, because I could choose this loop, and then this whole one, but then it gives me 2 redundant ones.
So right. Loop 1 is just that triangle?
Correct.
Oh, okay.
Right, I can't, you should not choose this triangle, and the big diamond, because then you forgot about the power supply. And then you'll have redundant loops. So R sub A is 1 ohm, R sub B is 1 ohm, R sub C is 1 ohm, R sub D is 2 ohms, and R sub E is also 1 ohm. Okay, so now let's apply the rule here. Okay, so I'm going to start. Let's start here. It doesn't matter where you start. I'm going to go around it. I'm going to go around that way. Okay? So I'll go, actually, let me go this way. So I'll start here, go around that way. So I'm saying I3 is in that direction. What can you say about the voltage drop? Positive or negative?
Negative.
Negative. So I3 times R sub B, I3 times this. That's the first one, because the resistance is 1 ohm. Then I get to this one. I2, I'm going against the direction of the current. That's the voltage gain. And then I go in this direction. I get a voltage drop. That's my first loop. Okay? Second loop. Second loop only has 2 resistors, just these guys. So let's start here. I go that way. I'm going to go clockwise this time. Again, it doesn't matter if I go clockwise or counterclockwise, as long as I use the laws of physics correctly. So let me go clockwise. I go from negative to positive, gain or loss?
Gain.
Gain, okay. And I'm going to be sloppy. I'm not going to use right units because of the fact that I'll probably run out of space.
Can you move the camera out a little more so we can see that whiteboard?
Sorry. Thank you. Is that okay?
Yep, perfect.
Okay, all right, good. And so which way were we going? We were going this way, and we hit this resistor. How much current is going through this resistor? I1. We're going in the direction of the current, so that's a voltage drop. And this is 1 ohm. 1 ohm times I1. I hit this resistor R sub C. How much current is going through it? This amount. I'm going in the I'm summing voltages in the direction of the current. That's the voltage drop. What's R sub C? 1 ohm?
Hey, Professor, shouldn't it be like the current value times the resistor?
What's the resistance value?
Oh, okay, never mind.
Okay. Yeah, one of them will have a 2 on it. The last loop will have one with a 2 on it. I picked these numbers just because it makes things a little bit simpler, that's all. Okay, and that's it, right? Last loop. Just a big outer one. So I'm including 2 loops with the battery. Okay? And it's not going to be redundant because it's going to include these 2 resistors, which are not included in this one. So again, I'm going to start here and go up. I'm going to have a 13 volt increase. I go around and hit R sub B. R sub B is 1 ohm. I get a voltage drop. Oh, R sub D is 2 ohms. I got one that's different. And since I'm summing voltages in the direction of current, that's a voltage drop. Okay, please don't try to solve this by substitution. Let me rewrite this. I'm going to rewrite them twice. Or maybe not twice. Let me just rewrite them. I'll rewrite them here. Hopefully I have enough space. I'm going to write the top one like this. I'm going to move this to the other side of the equation. And then how many I1s do I have here?
2.
2 of them? Hold on a second. What did I do wrong? Okay. I'm not sure what I did in my notes. I did something weird in my notes.
It is
Okay.
negative 2 I1, right?
I'm sorry?
Yeah. Yeah, negative 2 I1.
Okay. Yeah, for some reason, my notes I multiplied through by -1. I don't know why I did that. Okay, now the bottom one, I'm going to put this over here. Let's see, how many I2s do I have?
3.
Is that okay? All right. So, can I erase the circuit? Is that okay if I erase this?
Go for it.
Okay. I mean, this is essentially in your notes, so. Okay, so what am I going to do now? How am I going to solve this? So let me take these 2 equations, and I'm actually going to multiply the bottom one by -1. So let's take the 2 equations. I'm not going to use substitution. Okay. So let me take these 2. In fact, let me rewrite these 2.
Professor,
Yeah.
can't we just use matrices?
That's what I'm leading to.
Okay.
But not everyone's done that. I don't think everyone's had Math 33, unfortunately. Okay. Okay, and actually, let me write them all together. Hold on a second. Let me rewrite all of them. You notice how I wrote them, Ravtesh?
Yeah.
Okay. I'm going to take the second equation and just, multiply the second equation by -1. Okay. Suppose, what can I do with these? Suppose I add these two. What do I get? Suppose I add these two. Actually, hold on a second. I did something strange here.
You want to multiply the second equation by -1 and then add them, right? To cancel the I3.
Yeah, I'm sorry. I'm just I'm looking at my notes and I screwed something up in my notes. Sorry. Oh, okay. This is what I want to do. Can I multiply this top one by 2?
Yeah.
Now let's add these two. What do I get? That look okay?
Yeah.
So the next thing I'm going to do, I'm use a different color. Let me multiply, let me multiply this by 2 and this by 3. Notice I'm not using substitution. I'm just multiplying rows and really adding basically, I had them in columns. I'm multiplying by rows and just adding columns, okay, essentially. So what do I get when I multiply this by 2? I get minus 6i2 minus 4i3 equals, what is that, minus 26? And then this is going to give me 6i2 minus 9i3 equals 39. Add them. What do I get?
If we're given a problem like this, can we just use a matrix?
Yeah, you can. Again, I'm going to lead to that. Just hold on, and I'll lead to that.
Okay.
Okay. So I have a. Oh yeah, I'm going to add them. So let's add them. What do I get?
I3 equals -1.
And this just means that our guessed direction is wrong.
Correct. It's still, I still got the answer, it's just that the current goes in the opposite direction.
Yep.
Okay. I'm done now, right? Because then all I got to do is go into this equation, get I2, and then go into one of the other equations to get I1. Once I get this one, I'm done. Okay. I have everything I need now.
Wait, I don't get why how you went from I3 equals negative 1a to I equals negative 1a.
Oh, it should be a 3.
Oh, okay.
Okay, so I have all the equations in here, so let me go through real quick. I want to show you the final result. Oops. That's the final result. And so you're right. I just guessed the direction of the current wrong. The fact that I got a minus sign just says that I got the current direction wrong. Okay? Well, once I'm done with this, once I know this, I just need to go back to find I2. Software I2. I'll let you do that. And then you go back to one of the other equations in software I1, you're done. And then you can figure out everything. Notice, everything is labeled. I know everything. Once I get this, I'm done. All right, because I did the hard part. As long as those equations are correct, everything will follow. Then the rest is just making sure to make a silly algebra error, which I do a lot. Okay. So people were asking, what about matrix methods? So pay attention to, let me go back a slide. Hold on a second. Sorry I'm going so long. So what I have here, if you think about what I did, I can arrange these numbers. Let me get rid of these. In terms of a matrix, I can make this -1. All I gotta do is put the coefficients. Okay. All I gotta do is use the coefficients. All right, so I have that, and then I have this one. Doesn't matter how I put the rows. So 0, -3. Oops, I forgot something. -2, -13. So that's this one. Okay. And then I'm going to do this one. I already multiplied through by -1. 2, 0, -1, 13. And then what you can do, what did I do? I multiplied this by 2 and added it to this. So I can multiply this row by 2 and add it to this and get a new row. So the idea is you can manipulate the rows and columns just like you would when you solve them by multiplying rows and columns, normally, or multiplying equations and adding them. So you arrange the coefficients in terms of a matrix, and you can interchange two rows. You can multiply or divide a row by a non-zero constant. And you can add or subtract one row to another. In the same way as I solve the problem. The idea is you're getting what's called row reduction. So you take that matrix, you multiply 2 times row 1. That's what I did. If you remember what I did, I multiplied this by 2 and added it to this. and then I multiply one row by 2 and the other one by 3, to get that form. This is, so basically you're getting this staircase form. And so once I have 2 zeros up here, once I had those 2 zeros, that means I've eliminated 2 variables. So basically when I get these 2 down here to be 0, when I get both of these 0, then I know I have an equation that looks like this. I get minus 13 equals 13. That's basically, then I can just solve for I3. It's just another way of writing this. This is actually less writing than writing all the i's out. Okay. So this is the matrix form. So you guys, you folks who asked about matrix methods, this is what you were going to do, right?
Yes.
Okay. So you can do row reduction. There's also Kramer's rule.
Mm-hmm.
Okay. If you have a 6 by 6, if you have a 6 by 6, you'll actually want to do it on a calculator. Okay. I'm not going to give you a 6 by 6. At most, I'll give you a 3 by 3. So Michaela, I guess your question isn't it algebra. I'm not sure what you mean, what you're...
Oh, no. It's when you said that not a lot of people have had Math 33, and I was saying that I think they teach you that before Math 33, but I'm not sure.
Yeah, I don't know. I don't know if... Yeah, I don't know. I mean, I know it's taught in Math 33.
Yeah, I don't know. I wasn't sure, but I just remember because like when I took Math 33, they said that we should learn this a while ago. It was like a review kind of thing, but I don't know. I'm not sure. So.
Okay. Yeah, it might be taught. It's just that not everybody teaches. Not everybody takes. Not everybody gets the calculus the same way. So I'm just doing it that way. But if you want to use row echelon on an exam, that's fine. It's up to you. I can email you a handout on this stuff. Okay, from a textbook I have. It's and you can take a look at it. Okay. So all I want to do is, and I'm not gonna go through and solve it completely. I could show you a different way to designate the currents. Okay, so I'm just going to go through the slide, and you can go through the notes in their entirety here. I could solve the problem this way. There's the same circuit, okay? I'm going to designate I1 as I did before. I'm going to designate I2 as before. I'm going to designate I3 as before. I'm going to call that I4 and then I5. But I'm going to call the total current I4 plus I5. Okay? So I'm basically going to say that what's going through here is I4 plus I5. If I say that, then I1 ends up being I3 plus I4, and I2 becomes I5 minus I3. So my independent currents are I3, I4, and I5. And then I can apply the current rule, the loop rule to 3 different loops. That loop, and that loop. It doesn't matter what I choose. And solve the problem. And what you'll find, even though these numbers might be different, well, either even if these individual values might look a little bit different, the currents everywhere will be the same. You'll still get I3 as -1. You'll still get the same I1 as you had before, except that it'll be written in terms of I3 and I4. Okay. So I actually solved this using the other method. I set up the equations. And when you solve it, I had the note hidden. Hold on a second. Oh, it disappeared. There it is. When you solve it, you get I1 is still negative 1 amp, I4 is 7 amps, and I5 is 4 amps. And 7 plus 4 is 11. That's what you got before for I1 plus I2. Okay? So no matter how you designate the current, you got to get the same answer.
We cannot see your screen.
Oh. Every time I change something. Okay. So that's the set of equations, and then there's my final answer. I3 is negative 1, I4 is 7, and I5 is 4. And you can use the row reduction to solve that. And again, what I said before, the I4 plus I5 ends up being 11. That's what we had before. So I hid these in the notes because I usually don't have time to go through it. Although you guys have been patient enough to stay with me till now. So on Tuesday, all I'm going to do is the RC circuit and that example that I skipped. Okay, so I'm going to stop talking about Kirchhoff's laws and answer your questions that you have on the lab. Based on whoever's left. Are there any questions? Are we okay then? Because there was a bunch of questions at the beginning, so I just wanted to hold off on the questions till now.
In the capacitance worksheet, the one where you said that you had lambda, right?
Yeah.
So there, when you solve for capacitance, doesn't the lambda cancel out?
Oh yeah, you're right. Okay. And again, that's because of me hurrying. So you're right. Let's see. Let me just redo it real quick on the board. That's what happens when you're in a rush. Sorry. So delta V, if I remember correctly, was equal to 2k lambda natural log of R sub B over R sub A. And there's an L there too, right? Or no, it was like this. Sorry. Okay. And C is what?
Q divided by that thing. And then, yeah.
But I want the capacitance per unit length, right?
Mm-hmm.
So it's going to be lambda over delta V. See, this is what happens when I'm in a rush, sorry. And so that's going to be lambda over 2k lambda natural log of R sub B over R sub A. The lambdas cancel, and I'm going to get 1 over 2k natural log of R sub B over R sub A, the whole thing, because this is what Damien was talking about, to the minus 1. Okay. So yeah, it should be that.
Okay.
Okay?
Mm-hmm. And for the last part where the D is very much greater than R, is it fine if we just write like if D is very much greater than R, we can say D minus R is approximately D, and then we just replace it?
You know why I wrote D minus R? In the limits for integration? Yeah, you can say, that's fine, you can say, but you know what why I did it in the original worksheet?
Because it is changing only till the surface of the other sphere?
Yeah, and I don't want you to, because I don't want people to get the implication that you're integrating to the center of the sphere, that's why.
Mm-hmm. Yeah.
Okay, that's the reason why I put D minus R. Because if I just put D, students are going to say, oh, I integrate to the center of the sphere, why? So that's why I did it that way. But yeah, you're right, you can say that.
Okay.
Okay. Just realizing you're only integrating to the surface.
Mm-hmm. And this is only because they are conductors.
Yes, yeah.
Okay.
Because, I mean, the electric field inside is 0, right?
Mm-hmm.
Yeah.
And then if they were insulators, we would go till the center? No, okay.
Yeah.
Okay. It would be different for that, okay.
Yeah.
Yeah, okay, never mind.
Okay. Other questions?
For the Wheatstone bridge, but like in the case where the ammeter does not read 0, for that, like I was talking to my dad about it yesterday, and he was saying that the current would like see that, okay, before there is suppose 3 ohm resistance, and then after it crosses the ammeter there is 6 ohm resistance, suppose, in the other combination of resistors. So he said that when you have a combination of resistors, the sum which adds up to be the least, the current usually takes that path, and it does not go the other way.
Yeah, it's usually going to go along the path that has the lower resistance. You'll have more current along that path. I want to say it that way.
Mm-hmm.
You're going to have more current along the path of least resistance as opposed to the other path.
Mm-hmm.
That's true. I mean, we saw that in that example. A little bit harder. I mean, when you asked that question, it was harder to see what happened to the bottom part of the circuit. You can still get the same thing at the top part. When you do the bottom part of the circuit, given the numbers you're given, I have a little bit of a harder time seeing if I3 changes direction.
Mm-hmm. And then, like the resistances which are in the upper portion, is each resistance in series with the resistance on the other side of the ammeter?
Hold on a second. Let me draw that picture. That didn't work out. So I'm sorry, go ahead and say your question again.
So the resistances like R sub A and R sub B, can we say that R sub A is in series with R sub C and R sub D?
Well, these two are in series when the current through here is 0.
Mm-hmm. Yeah.
Yeah, when the current through here is 0, these two are in series and these two are in series.
And then if the current goes through the ammeter,
then you have then it's they're not in series, right? Because then the current here and the current here are not going to be the same.
Mm-hmm. Yeah, it diverges. Okay.
Okay.
Mm-hmm. Okay, so that is like when the ammeter shows 0 current, that is the only condition when they are in series?
Yes.
Okay.
Because if you have something going through here, then this current and this current can't be the same, right?
Yes.
Yeah. So yeah, this has to be 0. And you know, ideally, you really don't want to use an ammeter to do this. You want to use a galvanometer, although you can use the voltmeter, the current day voltmeters, because they have a high resistance.
Yeah, this was like one thing that I don't know, somehow I didn't get, is that we are using the same device as a voltmeter and as an ammeter, but at different settings. So internally, how does the voltmeter get so much resistance and the ammeter is ideally considered 0 resistance?
So, yeah, and I'm going to go by how things were done the old days. In the old days, you use a galvanometer, and you put a resistor in parallel to the galvanometer to measure current. And then you put that combination in series with your circuit. When you ran the galvanometer as a voltmeter, you put a galvanometer in series with some sort of resistor, and the value you choose for the resistor is important because it's gonna affect how much the galvanometer deflects.
Mm-hmm.
Okay. And so there you pick a big resistor, but then, you know, with how big of a resistor can you choose using the methods of the old days? So now you have solid state devices. You can make the resistance, you know, 100 million ohms. Okay. You're actually not putting a resistor, but using a solid state device to do it. But really, to measure, I mean, the simplest way to look at it is you use a galvanometer, put a resistor in series, and then put it parallel to your device. To measure current, you put a resistor in parallel. Let's call it a shunt resistor. And so I put a video on one of the modules where the electroboom, shows you how to do that.
Mm-hmm.
Okay, so when you take a resistor and you put it in parallel to the galvanometer or even the ammeter, that resistor is called a shunt resistor, and you can use it to measure current. And what that does is lower your resistance. And really what you're doing is measuring the voltage drop across that resistor.
So if like our voltmeter did not have high resistance, then the current would flow through it, and the potential difference across the 2 points where we connected it in parallel, that potential would not be the same as original?
Yeah, it would be messed up. So when we're on campus, if we were on campus, one of the parts of the Ohm's Law lab, what I would have you do is I would have you hook up this circuit. For part 1 of the Ohm's Law lab, one of the parts I have you do is I have you measure the voltage with a really old-fashioned voltmeter. That's 1,000 ohms. And this is 1,000 ohms. And guess what happens? This current changes because this guy is 1,000 ohms. I actually have you do that in the lab, so you get to see directly how the significance of having this being high when you're measuring voltage. So in the old days, you could not use a voltmeter here, but today you can. Because if you put 100 million ohms across these 2 points, it ain't going to affect the circuit.
Mm-hmm.
I mean, you're not going to notice it. But if you put 1,000 ohm meter here, you're going to notice it.
Yeah.
Okay. And if you take engineering 17L, he'll make you do a lab where you actually get to see the effect of the resistance of the meter. This one is so dramatic. I mean, your answer changes by a factor of 2 when you use this voltmeter as opposed to one that has 100 million ohm resistance.
Mm. Yeah, it was just that my dad, like, he's an electrical engineer. So I get a question